Hi, I'm Nat Jeffries, and this is the Gait anomaly detection monitor to prevent falls. So basically the project motivation is to keep track of people's gait as they are walking around, especially elderly people, and to help them avoid falling, because that's a big problem that they sometimes face. And falls are often not recoverable. They cause irreparable damage. So it's good if we can detect before somebody falls, when somebody's getting fatigued, when they're walking around, and alert them. That would be ideal. So some goals for the project are to give a high accuracy gait classification and detect anomalies, and also to have low latency, so you can generate alerts quickly as somebody's walking. Make it easy to use and comfortable to wear, which is something I addressed by making it a Bluetooth low energy module, which basically makes it very light and something small to wear. And my goal is to explore the effects of data quality and to figure out how that affects the classification accuracy. And so some design decisions were wired versus wireless. I chose wireless because it's much easier to wear. There's no wire going to the device. You don't have to carry your laptop around. The sensor location is another thing. I just decided to put it on the leg, on the ankle, because that's the highest signal that I could find. And it's a lot better signal to noise than somewhere like the waist or upper leg or arms, for example, when you're walking. And then the other thing is the location of the compute, which is actually being all done on the computer right now. Ideally, it could get moved to the device itself in the future, and that's something that I'm going to look into, or that might be looked into in the future for this project. So the architecture, basically, I use an Arduino using it's a blend micro board, which has a Bluetooth low energy module in it, and it also has an IMU attached to it, which does the measurement of accelerometer and rate gyro. It has a battery incorporated with it, so you don't have to connect it to anything for it to run. And the general control flow, the data flow, is it collects the data from the IMU. It goes to the Blend Micro. It sends it over the Bluetooth to my. It's a listener application on my computer, and then I read that into a MATLAB file and do the processing in MATLAB, and I do the data analytics and generate classification all on my computer on MATLAB. And so the experimental setup is basically to have a person do a training run, which is unencumbered. You have no weight on your leg, and you do it out and back, one out and back trial. And then you do a test run, and it checks how closely that matches the training run and does a classification based on that, whether or not it's good or bad. And this is just a very basic setup for this project, just to demonstrate that it works and that it's a proof of concept, basically. So in general, the data processing is being done in 3 different ways. So the first obvious thing that you have to do is separate out strides. And so I'm doing that, finding the maxes and mins in the data, in the gyroscope values, actually, to figure out when the leg's forward, when the leg's back, like that. And that can be seen with these 2 figures. And then I do stride length, and that only works with a high data rate, something that, for example, a wired setup could do. And so I managed to do that just fine and generate a stride length measurement, taking the double integral of the accelerometer in the forward direction. As the data rate decreases, you start to lose the peaks of the accelerometer, which means that your data becomes less and less accurate for stride length classification. And so that's why I went to stride evenness and curve fitting. So basically curve fitting, or stride evenness, I'll describe first, has 4 different segments of the stride. It's the heel strike, the mid stance, the early swing, and the mid through late swing. And you can see on this chart, it maps out where those are in the data. And you can find those and measure how long each segment takes, and then classify based on if those segments change in length relative to one another. You can classify it as an abnormal or an encumbered trial. And if they're very similar, it's an unencumbered trial. And also the curve fitting method basically fits a curve to that and then applies the curve and sees how different the trial is from the testing run, or from the training run. And so both of those are being used together to do the classification at the moment. So I've got the timeline here. There's not too much to say about this. I changed the sensor setup from the wired version, as you can see in version 1.0, to the wireless Bluetooth low energy one in version 2.0. The successful classification based on the version 2.0 came recently. So basically, the conclusions that you can draw from this are that high quality data can be gathered using this simple, very compact and light module. That Bluetooth low energy supplies adequate data to do classification, but that the data rate is too low for high quality classification based on stride length. So that's something, if we could improve the data rate, we'd be able to do better classification. many intuitive gait classification methods don't work as well as you might think, because gait changes naturally per person, depending on the run, depending on the situation. So it's very difficult to classify unless you have similar data sets, which is something I ran into. And so basically the future improvements are to increase the classification accuracy by increasing the data fidelity, and then also to reduce the classification latency by moving it to a cloudlet, for example. That would be another good improvement to do. If I could improve the BLE data rate, that would be great to get better data and for better classification. And then experiment with simplified classification where it could be moved all to the device. So for example, it could blink a light or have a speaker or something like that to tell you when your gait is changed. And then finally, I'd like to explore research possibilities with the data collected, because I've demonstrated this is great for collecting data. The hard part is using that data to do something meaningful. And so that's the roadmap ahead. This is my version 2.0 hardware platform. It's using Bluetooth Low Energy, and as you can see right now, it's on, it's recording values, and it's sending over Bluetooth so that a computer or another device could listen and could collect the data. Okay, as you walk, the device collects information and generates a CSV file on my computer, which monitors the accelerometer and gyroscope values on this device, and then allows it to be processed using MATLAB. In order to simulate fatigue, I'm adding a weight to my leg, which essentially makes my leg move more slowly. It's more difficult, and it's harder to get my leg off the ground, which simulates if somebody was becoming fatigued or having trouble walking. And so in this case, as you can see, my stride becomes uneven, and that represents, for me in my data sets, an encumbered trial. And so the previous trial was unencumbered without the weight leg, and this is encumbered. As you can see here, I've got a lot of raw data. It's very difficult to tell using the human eye what data corresponds to which gait, which stride. As you can see here, though, there is a pattern. It's a repeated pattern, which suggests that there's a very regular pattern to the stride. And I'll show you in a minute the classification based on this and which values I extract as valuable data to do classification for whether or not you have an encumbered or unencumbered trial. So as you can see here, I've got the data classification, and the trial in this case was encumbered, and so it's matching very well with the encumbered training data set, which is the blue and the red lines. And then the yellow line represents the unencumbered data set, which you can see has slightly higher values, which means your leg's moving faster or more easily, more freely. And the classification comes from the mean squared deviation between these two lines. So it's clearly being classified in this case as encumbered, which is correct.